An alloy mass weighing more than 100 tons, almost impossible to move on land, becomes the moving heart that silently carries an entire ship across thousands of nautical miles on the ocean. To shape this gigantic machine, everything must begin with a crude, full-scale wooden pattern. The factory must use hundreds of tons of sand to create the mold before pouring a batch of molten alloy at a temperature above 2000 degrees Fahrenheit. The liquid metal fills the mold in only a few minutes, but it takes nearly a week to cool completely. The casting then undergoes days of CNC machining, manual polishing, and laser scanning with tightly controlled tolerances. And right now, Factron Process will uncover the mysteries behind the creation of gigantic ship propellers, from a mass of molten alloy to its first rotation in the ocean. The ship propeller is one of the components rarely seen by passengers, yet it determines how efficiently a vessel uses the power of its engine. Since the 1830s, the first helical propeller designs were tested and gradually replaced the bulky paddle wheels on both sides of ships. Today, more than 112,500 merchant ships worldwide depend on these systems, creating a global marine propeller market worth approximately USD 4.85 billion in 2025, with North America alone contributing nearly USD 940 million. In the largest segment, each propeller can weigh around 251,000 pounds, equivalent to the combined weight of dozens of cars. Power from the engine is transmitted through the gearbox and tail shaft to the propeller hub. On a large cargo ship, the system can transmit more than 16,000 kilowatts, while the propeller rotates at only around 105 revolutions per minute. Although it turns slowly, each revolution pushes an enormous mass of water backward. Each propeller blade is precisely curved and inclined. As it moves through the water, the pressure difference between the two blade surfaces, together with the reaction force of the water pushed backward, generates the thrust that moves the ship forward. Before manufacturing begins, engineers must precisely determine the shape of each propeller blade to generate strong thrust while still saving fuel. Every design begins by reading operational data such as load, engine power, and shaft rotation speed. On ultra-large container ships, power can exceed 80,000 kilowatts. These are no longer lifeless mechanical figures, but a representation of how an enormous steel mass interacts with water under real operating conditions, where even a very small change can affect overall efficiency across millions of nautical miles. From this data, software creates a 3D propeller model and simulates water flowing across each blade. On the screen, the water current passing over every blade reveals regions where energy is lost or pressure suddenly drops. Cavitation appears at these points. The pressure falls so sharply that water boils even at normal temperatures, forming bubbles that continuously eat away at the propeller surface over time. Therefore, every twist, angle, and curve is rigorously examined in the simulation. A small adjustment becomes a difficult decision, aimed at optimizing efficiency and reducing hundreds of thousands of dollars in annual fuel costs. When the final design is approved, the factory begins constructing the enormous casting mold for the propeller. First, wooden boards are cut, joined, and ground according to every curve and twist angle to create a full-scale propeller pattern. The pattern is made slightly larger than the finished product to compensate for alloy shrinkage during cooling and to leave additional metal for machining after casting. The pattern surface is smoothed and then coated with a release agent because every raised mark can be transferred directly onto the casting. Heat-resistant sand is then placed in a mixer with industrial binder resin. The resin acts like an adhesive, transforming loose sand into a mass rigid enough to retain its shape against alloy heated above 1,100 degrees Celsius. The mixture is poured around the pattern in layers 10 to 15 centimeters thick. Workers use pneumatic rammers operating at a pressure of 6 to 8 bar, with steel ramming heads striking up to 1,000 times per minute, so the sand closely follows every curve of the blades. When the mold has hardened, the wooden pattern is removed, leaving behind a hollow cavity together with metal channels and ventilation holes. Even a small crack can become a defect, hidden deep inside the propeller. When the mold is ready, the metal ingots are weighed according to a formula containing approximately 80% copper, 9% aluminum, and 4% nickel, while the remainder consists mainly of iron, manganese, and several secondary elements. The mixture is loaded into an electric furnace and heated to around 2,000 to 2,140 degrees Celsius, causing tens of tons of solid metal to melt into a glowing stream of alloy. Sensors continuously monitor the temperature while workers remove the slag floating on the surface. Only when the temperature, cleanliness, and alloy composition meet the requirements is the pouring ladle lifted from the furnace and slowly transported toward the mold by an overhead crane. For a large propeller, this process may require 40 to 80 tons of molten metal. At the pouring position, a hydraulic or geared mechanism slowly tilts the ladle, releasing a continuous stream of alloy into the gating system. The metal gradually fills the hub and every propeller blade, while air escapes through the ventilation holes and the reservoirs continue supplying metal as the casting shrinks. Within only a few minutes, the entire alloy mass is contained inside the mold and begins solidifying into a gigantic propeller. Once pouring is complete, the gigantic mold remains inside the casting pit, so the alloy can gradually cool to a safe temperature. For a large propeller, this process may take around 5 to 7 days because the hub, which is several feet thick, always cools much more slowly than the blade edges. Only when the casting has cooled to a safe level do workers begin removing the mold, which may weigh hundreds of tons. In large factories, hydraulic excavators weighing around 50 tons dig out and move the hardened masses of sand, one by one. Heavy equipment can generate impact energy of around 8,000 to 17,000 foot-pounds per strike, enough to break apart the sand mass while still avoiding direct impact on the blades. When the mold is removed, the propeller emerges beneath layers of burned sand, black oxide, and excess metal around the hub. An overhead crane moves the casting to the cleaning area, where pneumatic hammers and vibrating equipment dislodge sand between the blades. The solidified pouring channels are cut away with industrial saws and ground smooth. Finally, abrasive blasting at around 80 to 100 psi removes the rough black layer, revealing the alloy surface and defects such as cracks, cavities, or unevenly cast areas. After cleaning, the propeller casting is placed on a large CNC machine. Based on the CAD design, the cutting head removes excess alloy and forms the curvature, twist angle, and thickness of each blade. The machine table rotates so the cutting tool can reach both faces, while coolant carries the metal chips away. When the shape meets the requirements, small tool marks remain on the surface, and the propeller is transferred to the grinding and polishing stage. After CNC machining, the blades have the correct shape, but are still covered with parallel tool marks. The worker begins with a coarse grinding disc, moving it across the surface in even and slightly overlapping bands. This movement removes metal evenly, prevents depressions from forming, and ensures that no area on the blade surface is missed. The first pass removes raised ridges and CNC tool marks. The following passes use finer abrasive discs to erase the marks left by the previous pass, connect the ground bands, and bring the entire surface to a uniform smoothness. The leading edge, trailing edge, blade tip, and the area connecting the blade to the central section receive the most careful treatment because even a small ridge can disturb the water flow and cause cavitation. The grinding process for a single large propeller can produce around 606 to 1,100 pounds of chips and copper aluminum nickel alloy dust. Large, clean chips from CNC machining are collected separately and returned to the foundry for remelting. Grinding dust mixed with abrasive material is captured by the extraction system and then transferred to a metal recovery facility, where impurities are separated before recycling. A 3D laser scanner collects millions of measurement points around the blades and compares the digital model with the CAD design. Areas with incorrect thickness, angle, or twist are returned for CNC machining or grinding, while deviations at critical locations are controlled to around 0.1 mm. Next, dye penetrant enters extremely small cracks and is drawn back to the surface by developer powder, allowing engineers to detect defects. Finally, the propeller is placed on an inspection shaft to measure concentricity and weight distribution between the blades before acceptance. Once inspection is complete, the propeller is placed on a multi-axle trailer and transported to the shipyard. The largest units can measure up to 36 feet across and weigh more than 251,000 pounds, so the load must be distributed evenly across the road. At the dry dock, a heavy-duty crane moves the propeller into position behind the hull. Workers check the shaft alignment, then use hydraulic jacks to push the propeller onto the shaft before securing it with a large nut. When the dry dock is filled with water, the propeller rotates for the first time at low speed, while engineers inspect the shaft seal, bearing temperatures, noise, and vibration. The ship then proceeds to sea and operates through several load levels as sensors record speed, shaft power, propeller revolutions, fuel consumption, and vibration. Only when the results match the design is the vessel accepted for its first commercial voyage. From an engineering model on a screen, the journey of creating a ship propeller begins with calculations involving engine power, rotational speed, vessel load, and the flow of water behind the hull. Every curve, angle, and blade twist must be carefully simulated because even a small change can affect thrust, fuel consumption, and vibration throughout the entire vessel. Once the design is approved, that shape is transferred into a gigantic casting mold made from hundreds of tons of heat-resistant sand. Copper, aluminum, nickel, and other elements are weighed in precise proportions and heated above 2,000 degrees Celsius. The solid metal ingots gradually collapse, merge together, and become a glowing stream of alloy. Within only a few minutes, tens of tons of molten metal fill the hub and every propeller blade. But inside the mold, the casting requires days to cool completely. The thin blade edges solidify first, while the thick hub continues to retain heat. This slow process forms the internal metal structure that will determine the propeller's strength throughout the years ahead. When the final layer of the mold is removed, the object revealed is still only a rough casting covered in burned sand, black oxide, and excess metal. The propeller continues through pneumatic hammers, industrial saws, abrasive blasting systems, and massive CNC machines. Layer after layer of alloy is removed until every blade reaches the curvature, twist, and thickness defined in the original design. However, machines still cannot complete the entire job. Skilled workers continue grinding and polishing every surface, especially the leading edges, trailing edges, blade tips, and the areas connecting the blades to the hub. They must remove machining marks without changing the hydrodynamic shape, because even a small ridge or an area ground too deeply can disturb the water flow and cause cavitation. A polished surface still does not mean the propeller is ready. A 3D laser scanner collects millions of measurement points and compares the actual shape with the CAD model. Areas with incorrect thickness, angle, or twist must be machined again. Dye penetrant then reveals extremely small cracks before the propeller is checked for concentricity and weight distribution between the blades. For a metal structure that can weigh more than 100 tons, even a small deviation can develop into continuous vibration after millions of revolutions. Each measurement is therefore not only intended to create a perfect surface, but also to protect the shaft line, bearings, hull, and every voyage ahead. Only after passing every inspection is the propeller transported to the shipyard. At the dry dock, heavy-duty cranes move it into position behind the hull. The shaft line is aligned, the propeller is pushed into place, and the entire assembly is secured before water begins filling the dock. For the first time since leaving the casting mold, the propeller begins rotating beneath the water. The engine is gradually raised through several load levels, while sensors monitor shaft power, revolutions, bearing temperatures, vibration, vessel speed, and fuel consumption. This is the moment when the entire manufacturing process is put to the test. A design on a screen has become a machine capable of receiving tens of thousands of kilowatts, pushing an enormous mass of water backward, and moving a ship weighing hundreds of thousands of tons forward. Throughout the voyage, almost no one sees the propeller. It remains deep beneath the surface, silently facing water pressure, corrosion, cavitation, and repeated loading with every revolution. Yet every nautical mile, every container, and every shipment crossing the ocean depends on the gigantic metal blades operating behind the hull. From sand, molten metal, and thousands of hours of machining, human skill creates a component powerful enough to move an entire floating city across the ocean. And when the vessel leaves the port, every sound of the factory disappears. Only the continuous revolutions beneath the sea remain, silently converting engine power into motion and keeping the flow of global trade moving. Subscribe to Factron Process to continue exploring the gigantic machines and industrial processes that silently keep the world running.